Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us to the edge of perception, to a place where golden petals opened in space and light older than Earth whispered secrets from the beginning of time. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the story of the James Webb Space Telescope and the galaxies that might be too old to be real. Let's begin not with science, but with a moment. A moment you may have missed in the blur of ordinary life, buried beneath errands and emails, beneath small joys and quiet worries. It was the morning of December 25th, 2021, while many people on Earth were opening gifts or sipping something warm. Far above the clouds, a different kind of present was unfolding. A telescope, not made of glass, but of gold and math and patient ambition, began its long journey away from us, toward the edge of Earth's shadow. Not to orbit our planet, but to escape its brightness, to flee the noise and heat and find a place dark and cold and steady, a place where it could see. That telescope was the James Webb Space Telescope, or JWST, if you prefer initials that feel a bit like a secret code. It didn't look like a telescope, at least not the kind we grew up drawing in school. It looked more like a golden flower, carefully folded, like an origami swan preparing to open its wings. It was launched aboard an Ariane 5 rocket, nestled gently in the payload fairing, cradled like a dream you hope doesn't break. And this dream had been a long time coming. Nearly 30 years of planning, redesign, arguments, tests, delays, hopes, and quiet recalculations. Thousands of people across dozens of countries had worked on this one delicate thing, a machine not designed to look at the moon or even the stars we can see, but to gaze into the earliest chapters of time itself. Its mission was as poetic as it was precise, to watch the faintest light from the farthest galaxies, from the earliest days after the universe began. And it does this by watching in infrared. While the Hubble Space Telescope gave us breathtaking images in visible light, the light your eyes already understand, JWST was built to see what's hidden just beyond, in the stretched out whispers of heat and glow that even our best lenses can't quite touch. Because as the universe expands, the light from distant galaxies is stretched along with it. What once was ultraviolet becomes visible. What once was visible becomes infrared. And what once was infrared fades into the radio hum of the cosmos. So, if you want to see the past, really see it, you have to look not just far away, but deep into the heat of forgotten light. JWST was placed not in Earth orbit, but at a gravitational balance point about 1.5 million kilometers away, called the second Lagrange point. You don't need to memorize that. Just imagine a place where Earth, the Moon, and the Sun all seem to cancel out each other's tug, like a silent corner of a vast room. That's where JWST sits, with its back to the Sun and its eyes to the dark. Its mirrors, plated in gold no thicker than a strand of hair, are designed not to shine, but to gather, to catch the faintest glow of galaxies whose light left them billions of years before Earth had oceans, or even atoms arranged into cells. These photons have been travelling longer than your family tree stretches. They left their home long before the word home meant anything at all, and now they arrive in silence, striking a golden petal in deep space. Imagine that! A piece of light, older than trees, hitting a mirror that didn't exist when it began its journey. It doesn't knock. It doesn't make a sound. It simply changes direction and tells us where it's been. That's what JWST is, a listener, not a speaker, a kind of celestial memory device, a way to see things that are long gone but whose light is still arriving just now. It's not time travel exactly, but it's close enough that the lines begin to blur. And the story it's about to tell us, that's what we're here for tonight. Because when those first images were released, they didn't just show us pretty galaxies and swirling dust. They showed us something unsettling. Galaxies that looked too grown up, too organised, too heavy, too old, as if the universe had cheated on its own schedule. But before we worry, before we wonder if our entire model of the universe is wrong, let's take a breath. Let's trace the journey from a telescope that bloomed in space to the galaxies it found and the ancient laws they might be bending. There's a story here, not of panic, but of curiosity, not of crisis, but of cosmic humility. So settle in. We're just getting started. If you had looked up at the sky on the day James Webb launched, you wouldn't have seen it. Not with your eyes, not even with binoculars. It was already on its way, far beyond the clouds, a golden secret gliding silently through the vacuum. But the real wonder wasn't the launch, it was what came after. You see, most telescopes are built solid, fixed, sturdy. They leave Earth as they intend to work. But JWST couldn't do that. It was too large, too intricate, too sensitive. So it had to be folded, like a puzzle, like a paper swan tucked into a matchbox, its delicate wings bent and packed inside the rocket fairing, barely fitting. Every layer, every hinge, every sunshield and sensor held in place by tension and faith. And for the first few weeks after launch, humanity held its breath. Because the telescope didn't simply turn on, it had to unfold piece by piece, command by command. Over 300 individual actions had to occur, most of them one time only. There were no backups, no second chances. A stuck latch, a misfired motor, a flap that didn't quite lock, and it would have been over. Decades of work, lost in silence. But the universe, perhaps moved by patience, allowed the ballet to proceed. First came the sunshield, a 5-layered kite the size of a tennis court, unfurling not to catch the wind, but to block it entirely. This enormous silver petal would protect the telescope's mirrors from the heat of the sun, earth and moon, allowing its sensors to remain colder than frozen nitrogen. Not just cold, but colder than space itself. This chill was essential. Only in the dark could the faint warmth of ancient galaxies be detected. Then the secondary mirror extended, delicate and round like an eye on a stalk. It perched in front of the primary mirror, waiting to catch and focus the light like a hand gently redirecting a stream. And then, slowly, majestically, the primary mirror unfolded. 18 hexagonal segments clicked into position, aligning their golden faces until they behaved like a single surface, each segment just under a meter wide, each one adjustable by microscopic motors. Together they formed a flower of precision, a golden eye more powerful than anything ever sent into space. It was not flashy, it was not dramatic in the way fireworks are, but for astronomers, and for all those quietly watching, it was transcendent. The universe had handed us a mirror, and we had dared to build it ourselves. But what would it see? The James Webb Space Telescope is not just another telescope. It is not there to take prettier pictures of things we already know. It was designed to answer questions we've barely begun to ask. Questions like, what did the very first stars look like? When did the first galaxies assemble? Could we detect the faint fingerprints of life in the atmosphere of an exoplanet hundreds of light years away? To do that, it needed to see in infrared. Now, infrared might sound technical, but think of it like this. It's the kind of light that glows from warmth. You don't see it with your eyes, but you feel it when you put your hand near a stove or bask in the late afternoon sun. Objects that are too cool to emit visible light dust clouds, distant planets, ancient galaxies still shine in infrared, and the further away something is, the longer its light has travelled, and the more that light is stretched into this deeper spectrum. So JWST doesn't just see far, it sees deep. Deep into time, deep into formation, deep into the folds of what was once invisible. And because it is so distant, 1.5 million kilometres from Earth, it avoids the heat and light pollution of our planet. It lives at what's called the second Lagrange point, or L2, a kind of gravitational sanctuary where the Earth and Sun's pulls balance out just right. It's not so much a location as it is a relationship, a place where balance allows stillness. There, the telescope sits behind its silver shield, always facing away from the sun, always gazing outward. It doesn't spin or tumble, it holds steady, like someone listening for a whisper in the middle of a storm. From this quiet vantage point, it began its mission. In its first weeks of calibration, JWST turned its eyes to a star, just one, and the results were astonishing. The star, 2-mass JWST faces 4042, 6 based on Centium, would have been unremarkable in most telescopes, but in JWST's mirror it became a blazing jewel surrounded by galaxies in the background. Galaxies that were not the subject, but the scenery. Just background. Just there. Dozens of them. Spiral, elliptical, irregular. Not in the image's centre, not the focus, just casually present. That was the first hint. The telescope hadn't even started working properly, and already it was seeing deeper than anything ever had. And as the images kept coming, sharp, clear, golden, they revealed something strange, something unexpected. Galaxies that looked too organised, too heavy, too mature, as if the universe had gotten ahead of schedule, as if time had passed faster in some parts of space. It wasn't just beautiful, it was puzzling, because these galaxies weren't supposed to exist yet, not according to our models, not this soon after the Big Bang, not with this much structure, this much dust, this much light. It was as if you opened a baby book and found a photo of the child already wearing glasses and holding a college diploma. But we'll get there. We'll look at that mystery soon. For now, just rest in the idea that we have built a mirror so precise, so delicate, so finely tuned, that it can catch the glow of galaxies older than memory, that it sits in the stillness beyond Earth, waiting for light so faint it could be mistaken for nothing. But it is not nothing. It is the story of everything. It was July 2022. Scientists gathered silently thrilled as the first deep images from the James Webb Space Telescope arrived. These were not just test shots. These were carefully chosen glimpses into the oldest corners of the universe, the farthest reaches of distance and time that human hands had ever reached toward. And while the images were undeniably beautiful, shimmering galaxies, curling nebulae, the soft swirls of cosmic dust, there was something else in them too, something quietly unsettling, a whisper, almost, a hint that the universe was not quite playing by the rules. Among the galaxies JWST spotted were some that didn't look new. They didn't look like they had just emerged from the cosmic nursery, blinking and chaotic, still warming to the light. Instead, they looked old, massive, structured. Some were shaped like discs. Some already held the dusty fingerprints of stars that had lived and died, and that wasn't supposed to be possible. You might imagine that in the early universe, just a few 100 million years after the Big Bang, galaxies would still be forming, like paint swirling on the surface of water. They should have been small, irregular, clumpy. The stars inside them should have been few, and fresh, and mostly made of hydrogen and helium, nothing more. After all, those first stars, called Population 3 stars, lived fast and died violently, seeding the cosmos with heavier elements. But in those early galaxies spotted by JWST, there was evidence that the story had already progressed, that chapters had been written, edited and rewritten long before we expected them to even begin. Some of these galaxies showed signs of chemical enrichment, meaning elements heavier than hydrogen and helium had already formed and spread. Others displayed structured shapes like spirals or disks, requiring time and gravity and relative peace to settle into such order. And perhaps most perplexing of all, a few appeared to be simply too massive, too many stars packed into a single structure, too soon. It's as if you opened a photo album expecting baby pictures and found portraits of grandparents instead. As if the universe had skipped some of its childhood, arriving early to maturity. Galaxies with wrinkles, with taxes, with mortgages. And we were left wondering how they got there. Astronomers speak in redshifts, numbers that describe how much the light from a distant object has stretched as the universe expands. Higher redshift means farther away, and farther away means further back in time. The galaxies JWST was seeing had redshifts above 10, even 12, meaning they formed just 300 to 400 million years after the Big Bang. That's young in cosmic terms. Too young, it seemed, for this level of complexity. For decades, cosmology has rested on a model, a kind of story the universe is thought to follow. It's called lambda CDM. Lambda refers to dark energy, and CDM stands for cold dark matter. This model says that small structures formed first, merging slowly over time to create the large, beautiful galaxies we see today. It paints the early universe as turbulent, rough and full of little fragments slowly colliding and assembling. That story has worked well. It's supported by many lines of evidence, from the cosmic microwave background to galaxy surveys to simulations that model how matter should clump over time. But these new galaxies from JWST, they didn't fit. They weren't small, they weren't chaotic. They didn't seem to be fragments, but finished works. Maybe not complete novels, but certainly not rough drafts. And so, murmurs began to spread. Were the models wrong? Had we misunderstood the timeline? Was the Big Bang itself misdated or incomplete in our understanding? Some people, especially in headlines and tweets, called it a crisis, a breakdown, as if the foundations of cosmology had begun to crack. But that's not how science really works. Not in quiet observatories, not in the minds of those who spend their lives listening to the stars. What scientists felt mostly was curiosity, and maybe a little embarrassment, because the universe had once again done what it always does. It surprised us. It had told a story we weren't expecting. Still, surprise is the beginning of all true understanding. And so, the questions began. Were these galaxies really as old and massive as they seemed? Were we measuring their light correctly? Were we making the right assumptions about the stars inside them, their size, their temperature, their age? Was it possible that a different kind of star formation had taken place in those early epochs? One more violent, more efficient, more hurried than we had imagined. In some ways, the galaxies JWST found didn't just challenge our models, they challenged our sense of timing, of pacing, of what is considered enough time for something to become something else. Maybe the early universe was simply more eager than we thought. Maybe gravity and matter and radiation formed partnerships more quickly than we had accounted for. Or maybe we've just been looking with the wrong tools until now, trying to read a distant message with smudged glasses. And now, with JWST's clear eye, we're finally seeing what was always there. It's humbling, isn't it? To realise that the cosmos may be older and younger than we know. That light can arrive wearing disguises, that some stars might burn through their lives before we even finish asking the question of how they were born. But this isn't the end of the story. It's just the part where the mystery begins. We're not looking at a failure, we're looking at a beginning. And beginnings, especially the cosmic kind, are full of wrinkles. When something doesn't match what we expect, we have a choice. We can cling more tightly to what we thought was true, insisting that reality must be mistaken. Or we can loosen our grip, soften our gaze, and allow wonder to guide us into new territory. That's the path science tends to choose, not always immediately, not without friction, but eventually it bends toward curiosity. And this moment, brought to us by the James Webb Space Telescope, is no different. The galaxies that appeared in JWST's first deep images, those oversized, well-behaved structures glowing just a few 100 million years after the Big Bang, were unexpected, yes, but they didn't break the universe. What they broke was the neatness of our mental map, a model, specifically the one called lambda CDM. You don't need to memorize the name. It sounds a bit like a code or a pharmaceutical brand, but really it's just shorthand for the story cosmologists have been telling for the past few decades. Lambda stands for dark energy, a mysterious force that causes the universe to expand faster and faster, as though space itself were stretching gently apart. CDM stands for cold, dark matter, which provides the invisible scaffolding that holds galaxies together and seeds the large-scale structure of the universe. Combine these two, and you have a model that's surprisingly good at explaining the shape, structure, and evolution of the cosmos from its earliest moments to now. According to this model, the early universe was a hot, dense, and nearly featureless soup, mostly hydrogen and helium, with tiny quantum ripples baked in during the first fraction of a second. Over time, these ripples grew under the force of gravity, creating little pockets where matter clumped. These clumps merged to form bigger clumps, which in turn formed small galaxies, and eventually larger ones. It's a slow, stepwise process. You start small, you build up. The universe, in this story, is a patient architect. So when JWST showed us galaxies that already seemed large, organised, and chemically mature in the universe's infancy, the story wobbled. It didn't shatter, but it blinked. The standard model didn't predict this kind of cosmic efficiency. These galaxies weren't just a little ahead of schedule, they were chapters ahead, as if someone had skipped a few pages. But that's the thing about models. They aren't reality. They're approximations. Maps, not the territory. And like any map, they depend on assumptions about how stars form, how galaxies grow, how dust and gas behave, how light changes as it travels through time. If any of those assumptions are even slightly off, the predictions shift. One major assumption baked into our models is about something called the initial mass function, or IMF. It's a statistical guess about how many big stars versus small stars are born in a typical batch of star formation. In modern galaxies, most stars are small, long-lived, and relatively cool. But what if the early universe favoured more massive stars, bright, hot, and short-lived? If that's the case, then galaxies might shine more brightly than expected, making them appear more massive than they actually are. What JWST might be seeing isn't a galaxy with too many stars, but a galaxy with fewer, brighter ones than our models accounted for. There's also the possibility of observational bias. JWST is incredibly sensitive to infrared light, which makes it especially good at detecting galaxies that are dusty, star-forming, and actively glowing in that wavelength. In other words, it might be picking out the cosmic overachievers, the galaxies that formed stars quickly, burst brightly and faded early. Maybe they're the exceptions, not the rule. Like stumbling upon a handful of child prodigies and assuming every toddler must play Mozart. And then there's the trickiness of interpreting light across billions of years. The galaxies JWST sees are so far away, their light has been stretched, scattered, and transformed by cosmic expansion and intergalactic dust. Scientists use complex models to reconstruct what that light means, estimating distances, masses, star populations, and chemical content. But small uncertainties in those models can produce large differences in the conclusions. So some of what we're calling too old might just be less well understood. Still, even with all that's said, even with caution and recalibration, and the knowledge that early results are always refined over time, something about this feels important. These galaxies aren't just numbers, they're messengers. Their light has crossed a vast and changing universe to reach us. And what they're telling us is simple. The universe might be more complex, more flexible, and more creative than we expected. But that's not a crisis. That's a gift. It's tempting in moments like this to reach for big conclusions, to declare that everything we thought we knew is wrong, to rewrite the textbooks in a flourish. But science doesn't work like that. It's not built on drama. It's built on patience, on listening, on revising slowly, carefully, with the humility that comes from knowing the universe is under no obligation to make itself easy to understand. And so, the cosmologists went back to work. They re-examined their assumptions. They ran new simulations. They considered new kinds of stars, new types of dust, new patterns of galaxy formation. And they asked the question that defines all good science. What else might be true? Because this isn't the first time a telescope has surprised us. Hubble did it. So did Galileo. Every new lens we've ever built has shown us things we didn't expect. That's not failure. That's how progress looks from a distance. In a way, JWST isn't just showing us distant galaxies. It's holding up a mirror to our models, our ideas, our need for neatness. And it's reminding us that the universe is not here to comfort our assumptions. It's here to astonish. So as we move forward, let's not fear the mismatch between model and mirror. Let's be grateful for it. Because in that small gap, in that wrinkle of understanding, is where discovery lives, and the universe, it seems, is still very much alive. To understand what came, before galaxies, before stars, before even the glow of ancient light, we must step softly into a time before time meant anything. A time without clocks or constellations, without motion or memory. A time when the universe, as we know it, had not yet begun its slow unfolding. But it did begin, somehow. And though the exact moment may forever be cloaked in mystery, the story that follows begins with something very small, very dense, and very hot, then expands suddenly, incredibly, into something vast. This moment is what we call the Big Bang. Not an explosion in space, but the beginning of space itself, stretching outward in every direction. In the tiniest sliver of time imaginable, the universe expanded faster than the speed of light. This phase is known as inflation. Not like the inflation you hear about in economics, but rather a kind of ballooning so rapid and extreme it defies intuition. A universe that went from smaller than an atom to larger than a galaxy in less than a blink. It didn't expand into anything. There was no outside. There was only expansion itself, pure becoming, like breath drawn in before a thought. But even in this earliest of moments, there were tiny imperfections, little fluctuations, random quantum jitters at the smallest scales, uncertainties written into the very fabric of space. These weren't mistakes, they were ingredients. Because when inflation occurred, these microscopic jitters were stretched across the cosmos, frozen into place like fingerprints on soft clay. They became the seeds from which everything else would grow. Think of it like this. Imagine a still pond, perfectly calm. Now toss in a few pebbles, gentle ones, the kind that barely ripple. If the pond were suddenly frozen, those ripples would stay carved into the surface. Now imagine those tiny waves not on water, but on the fabric of space itself. And you begin to sense what happened during inflation. Those ripples, barely there at first, eventually became the outlines of everything, the scaffolding of galaxies, the places where matter would gather and light would dance. From nothing in particular, structure began to emerge. After inflation slowed, the universe continued expanding, but now more gently, more steadily. It was filled with a hot plasma of particles and energy, too hot for atoms to form, too dense for light to travel freely. This phase, often called the primordial soup, was a fog. Light and matter bounced constantly off each other. The universe glowed, but blindly. Everything was illuminated and nothing could be seen. And yet in this fog, The imprints of those original ripples remained. They weren't erased by heat or motion. They were baked into the temperature, into the density, into the destiny of space itself. Over time, as the universe cooled, the fog began to thin. Electrons found protons. Atoms formed. Light, at last, was freed. This moment is known as recombination, and the light from it still fills the universe today. It's what we call the cosmic microwave background. A baby picture of the cosmos still visible in every direction if you know how to look. But long before JWST opened its golden mirrors, long before galaxies spiraled and stars burned, these ripples had already written the outline. The map was set. The blueprint of where gravity would gather matter, where gas would pool, where stars would eventually ignite. And yet, in those first few 100 million years, not much had taken shape. The universe remained dark, quiet, and unstructured. The fog had lifted, yes, but the light we now think of as stars had not yet begun to shine. This period is sometimes called the Cosmic Dark Ages, not because it was sinister, but because it was literally dark. No stars, no galaxies, just slowly drifting hydrogen and helium, cooled and patient. Still, the ripples endured. Where they were slightly denser, gravity pulled a little harder. Like the beginnings of valleys in soft terrain, matter flowed toward these low points. Clumps began to form, gas gathered, and somewhere, in one of those first clouds, the first star began to take shape. But we'll get there in a moment. For now, rest in this strange idea that everything we see, the galaxies, the planets, the light that reaches your eyes or the telescope's lens, came from tiny quantum flickers, random fluctuations stretched across a newborn universe, noise becoming structure, fog becoming form. This isn't just theory, it's something we can see. The patterns of temperature in the cosmic microwave background, the faint mottling you'd notice if you looked closely enough, match the predictions made by inflation and quantum fluctuation theory. The ripples were real, they were gentle, but persistent, and over billions of years they shaped everything. In the hush that followed the Big Bang, the universe was not empty. It was full of potential, like a field just before the wind moves through it, like a thought just before it becomes a word. And it's in this hush, this deep and ancient stillness, that the first lights were about to awaken. So far, the universe has been a quiet place, not empty, but unfinished. For hundreds of millions of years after the Big Bang, it remained dark, filled with hydrogen and helium gas, drifting through vast distances under the gentle guidance of gravity. There were no stars yet, no galaxies, no shining, just a deep and patient night. But that was about to change. Somewhere in that soft darkness, a region just slightly denser than its surroundings began to feel the weight of itself. Gravity, ever patient and invisible, pulled gas inward. Slowly at first, and then with growing insistence it collapsed. The hydrogen gathered, compressed, and heated. The atoms began to move faster, to collide harder, until something extraordinary happened. Something that had never occurred before in the history of everything. A star was born. We don't know its name. We don't even know where exactly it was. But we call it one of the first, a member of what astronomers call population 3 stars. These were the pioneers of light, the first fusion engines to ignite in the cold fog of the early cosmos. And they were not like the stars we see now. Today's stars, our sun included, are made not just of hydrogen and helium, but also of heavier elements like carbon, nitrogen, and oxygen. These elements don't appear by themselves. They are forged in the hearts of stars and released when those stars die. But population 3 stars were made from the untouched matter of the Big Bang. Pure hydrogen, pure helium, untainted by the lives and deaths of earlier generations. They were the first attempt at starlight, raw and unrefined. And they were big. Enormous, in fact. Models suggest they may have been hundreds of times the mass of our Sun, burning hotter, faster, and brighter than anything we know. But their brilliance came at a price. Massive stars live short lives, some just a few million years. Then they die in explosions more powerful than words can quite describe. Supernovae, collapses, bursts that send shockwaves through space and enrich the surrounding gas with the first heavy elements. In their deaths, these first stars gave the universe its first breath of complexity. The oxygen you breathe, the calcium in your bones, the iron in your blood. None of it could have existed without them. They did not live long, but they changed everything. And in doing so, they ended the cosmic dark ages. You see, before the first stars, the universe was not just dark. It was opaque. The leftover fog from recombination still filled the space between atoms. But when stars began to shine, they released not only light but radiation. High-energy photons streamed out, ionizing the gas, stripping electrons from atoms, and transforming the opaque fog into something transparent. This process is called reionization, and it's how the universe became visible. But here's the challenge. We've never directly seen a population 3 star. They burned hot, lived fast, and vanished long ago. Their light, if it ever reached us, has been stretched by cosmic expansion into the deep infrared, faint, elusive, and easily drowned out. Even the mighty Hubble Space Telescope was not sensitive enough to find them. But James Webb was made for this. With its finely tuned infrared sensors and cold, silent position in space, JWST was built to catch the afterglow of these ancient fires. Not to see the stars themselves, perhaps, but to see their fingerprints, their influence, the changes they left behind. A patch of ionized gas here, a sudden bloom of heavier elements there, galaxies that formed from their ashes, richer and more structured than the gas around them. If it can find these signs, if it already has, then we may be closer than ever to witnessing the moment light first broke the stillness. But even if we never see them directly, we can imagine that first star. Not the biggest, not the brightest, but the one that mattered. The one whose fusion ignited not just atoms, but the beginning of story. Its light would have spread through the surrounding darkness like a single candle in an endless cave, illuminating particles that had never before felt illumination. No planet circled it. No eyes watched it rise or set. But it burned nonetheless, because that is what stars do. And then it died. Not quietly, but spectacularly. Its end was not a silence, but a scattering, a dispersal of all that it had made within itself. And those scattered pieces became the seedbed for everything else. That is what makes these first lights so sacred. They were not observed. They were not remembered. But they made remembrance possible. They gave the universe its contrast, darkness and brightness, silence and song. Before them, the universe was a whisper. After them, it had begun to speak, and that's what James Webb is listening for. Not just brightness, but memory. Not just light, but the first moments when light became meaning. It's like walking into an ancient forest and listening for the first bird that ever sang. You'll never hear it, but you might hear its echo, bouncing between the trees. So sleep now, if you like, under the thought that stars once lived and died before time had a name, that their fire still echoes, that we are, in some quiet way, their descendants, not just in chemistry, but in wonder. Because the first lights in the mist are not gone. They are carried forward, in dust, in memory, in us. Once the first stars had lived and died, burning through their brief luminous lives and scattering their contents across the cosmos, the universe began a new chapter. It had moved beyond silence, beyond fog, into something more complex. It was no longer simply expanding, it was beginning to gather, to organise, to form relationships between matter and motion. And from these relationships, the first galaxies were born, but they didn't arrive fully formed. They didn't spiral elegantly or shine with grace. At first, they were more like embers than flames, scattered clusters of stars held loosely together by gravity and proximity. No grand disks or bulging cores, no sweeping arms or central black holes. Just groups of stars sharing a gravitational fate, drawn to one another like fireflies blinking across a summer field. These early galaxies were small, perhaps only 1,000th the size of the Milky Way. They were often chaotic, their shapes irregular, their stars formed in bursts and then silence, like breaths taken with hesitation. But despite their simplicity, they were foundational. They were the scaffolding from which all larger structures would eventually emerge. Over time, these small galaxies began to interact. Some drifted past one another in silence. Others collided, gently at first, and then more violently. Mergers were common. They weren't cataclysmic in the way we might imagine, with stars crashing into stars. Space, after all, is mostly space. But the gravitational influence of these mergers stirred the gas inside each galaxy, compressed it, ignited new waves of star formation. Galaxies didn't just grow by making more stars, they grew by combining with each other, like rivers merging into larger flows. This process of accumulation, of small becoming large, of simple becoming complex, is called hierarchical formation, and it's a core idea in modern cosmology. The universe didn't build everything at once. It started with fragments. It let those fragments find each other, slowly, across millions and billions of years, and from their unions came the galaxies we see today. In this way, the early universe resembled a vast workshop, one that was not rushed, but patient, not chaotic, but improvisational. Galaxies were not assembled on a production line, but woven together in an endless collaborative tapestry. Each interaction, each collision, left behind a signature, new stars, new shapes, new directions. And while this was happening on small scales, something even larger was taking shape. You see, matter in the universe does not scatter randomly. Thanks to the ripples seeded during inflation, matter followed patterns, regions of slightly higher density, where gravity pulled more strongly, drawing gas and stars inward. These regions stretched across vast distances, connecting the universe like threads in a web. Over time, these threads became filaments. The low-density regions became voids, and the result was something breathtaking, the cosmic web. The cosmic web is not a metaphor, it's a real structure, enormous, delicate, and intricate. Galaxies cluster along filaments, forming bridges between larger nodes where galaxy clusters gather like knots. Between these filaments lie vast, empty regions, cosmic deserts where few galaxies reside. The web is the universe's large-scale architecture, a record of both its origins and its ongoing dance of matter and motion. In this web, galaxies are not isolated. They are connected. They feel the gravitational pull of their neighbours. They flow along the filaments like dew sliding down threads of silk. Even the emptiest parts of the universe are shaped by this pattern. It is everywhere, whether we see it or not. The James Webb Space Telescope, though not built to map the web directly, plays a role in revealing its earlier scaffolding. By observing galaxies as they appeared billions of years ago, JWST helps us trace the early strands of the web, the first clustering of matter into form. It lets us see not just where galaxies are, but where they were and how they were shaped by the currents of structure flowing through the cosmos. And those early galaxies, the scattered sparks, were more than just stepping stones. They were laboratories. Inside them, the second and third generations of stars began to form. These stars inherited the enriched gas left behind by their ancestors. They burned with more stability, lived longer, and in some cases formed planets. Perhaps somewhere in one of those early galaxies a planet was born. Maybe it was rocky. Maybe it had water. Maybe it orbited a quiet star and held the ingredients for life. We can't know, but we do know this. Everything that makes life possible, the carbon, the nitrogen, the oxygen, came from stars that lived and died in galaxies like these. Galaxies that flickered faintly in the dark, billions of light years away before our sun was born. And so, what began as scattered sparks, tiny fluctuations magnified by time, became the glowing cities of stars we see now. Galaxies that rotate and evolve, that dance and devour, that light the sky with beauty and burn with memory. Their story is one of becoming, from ripples to stars, from gas to light, from fragments to form. And in that story you are not separate. You're made from the ashes of stars that lived in these early galaxies. You're shaped by the gravity that once pulled gas into clusters. You're not watching the story. You are part of it. So as you drift towards sleep, imagine those scattered sparks still glowing, faint but steady, across the dark canvas of time, and know that some of their light may still be on its way, still travelling, still unfolding, not lost, just delayed. Long before James Webb opened its golden petals to catch the whispers of ancient light, long before galaxies were weighed or redshifts measured, there was only the sky. And for most of human history it was a sky we watched with nothing more than our eyes and our imaginations. No telescopes, no sensors, no maps etched with galaxies, just the slow movements of stars overhead, the rhythms of sunrise and sunset, and the stories we told to make sense of it all. The stars were patterns, shapes, clocks, gods. Farmers read them to decide when to plant. Sailors steered by them across dark waters. Children watched them flicker and dreamed that each one was a soul. And though these stories were varied and often poetic, one belief was nearly universal, that the sky was unchanging, eternal, a fixed backdrop where only the moon and planets wandered. The heavens, it was said, were perfect. And then someone built a telescope. It was 1609 when Galileo Galilei, an Italian mathematician with an eye for mischief and lenses, turned his handmade telescope toward the moon. He hadn't invented the telescope. Simple spyglasses had existed for a few years already, but he was the first to point one skyward with scientific intent. What he saw was not divine perfection. It was surprise. The moon, once imagined to be a smooth, luminous sphere, was scarred with craters and shadows. Jupiter, the wandering star, had moons of its own. 4 bright specks that danced around it like children orbiting a parent. And Venus went through phases like the moon, revealing its path around the sun. These observations didn't just reveal new facts, they shattered old beliefs. The universe, it turned out, was not centered on Earth. It was not fixed nor perfect. It was active, layered, complex. The telescope had not just magnified distant objects, it had altered our sense of place. And the glass that did it? Simple, ground by hand, barely the width of your palm. Imperfect by today's standards, but powerful enough to change everything. From that moment on, the telescope became humanity's time machine. Not in the way of science fiction, with buttons and gears and paradoxes, but in a quieter, more reliable way. Because the farther you look, the older the light you see. A star 100 light years away shines with light that left it when your great-grandparents were children. A galaxy 1 billion light years away. Its light began travelling before mammals had taken hold on Earth. To look outward is, in every sense, to look back. And as our tools improved, so did our reach. In the centuries that followed Galileo, telescope design evolved. Mirrors replaced lenses. Domes were built on mountaintops to escape the shimmer of atmosphere. Photographic plates replaced the eye, then gave way to digital sensors. Telescopes grew larger, more precise, more ambitious. They tracked comets, mapped the orbits of planets, and revealed that our Milky Way was just one among countless galaxies. One of the most transformative of these modern instruments was the Hubble Space Telescope. Launched in 1990 and orbiting above the blurring atmosphere of Earth, Hubble offered a view that was clearer than anything ground-based telescopes could achieve. Its images of nebulae, exploding stars and galaxies billions of light years away captivated the public and reshaped astronomy. Perhaps its most iconic contribution came in the form of the Hubble Deep Field, a long-exposure image taken in 1995 by pointing the telescope at a tiny patch of sky that appeared, at first glance, to be utterly empty. Over 10 days the telescope gathered light from this dark corner, collecting photons one by one, and when the image was processed it revealed something astonishing. Thousands of galaxies, each a swirling city of stars where before we'd seen only blackness. It was a revelation, not just of quantity but of possibility. If that one small patch of sky held so much, then how much more must there be? The answer, of course, was staggering. But even Hubble had its limits. It could not see deep into the infrared. It could not peer as far back as scientists hoped. It struggled to detect the light from the first galaxies, the earliest stars, the moments closest to the beginning. It was brilliant, but it was not the end of the story. It was a bridge. And across that bridge, James Webb was waiting. JWST was conceived not to replace Hubble, but to extend its reach, to continue the journey further into the dark, where Hubble captured visible and ultraviolet light. Webb would specialize in infrared. It would look through dust, through time, into the cooled and stretched wavelengths of the universe's childhood. But none of this would be possible without the quiet revolution started by a piece of glass held in trembling hands over 400 years ago. The history of astronomy is not just a timeline of discoveries. It is a story of lenses, of mirrors, of instruments designed to do one extraordinary thing: collect light, to take what is faint and far and bring it near, to make the invisible visible, and in doing so, to remind us that knowledge is not just about knowing. It is about seeing, gently, clearly, and with humility. So tonight, as you lie beneath whatever sky stretches over your part of the world, know that the photons touching your skin were once part of this journey. That light, old and young, surrounds us, and that glass, curved just right, still changes everything. Every eye, no matter how clear, eventually reaches the edge of what it can see. And when the Hubble Space Telescope opened its eye above Earth in 1990, it did something remarkable. It looked not just farther than we had ever looked before, but with a kind of clarity that made the cosmos feel close. What had once been smudges became spirals. What had once been darkness revealed structure. And what had once been theory about the age of the universe, the rate of its expansion, the makeup of galaxies, became observation. But perhaps the most poetic thing Hubble ever did was to look at nothing. In 1995, astronomers pointed Hubble at a patch of sky near the Big Dipper. It was tiny, about the size of a grain of sand held at arm's length, and, by all appearances, empty. No known stars, no obvious galaxies, just blankness. But they let the telescope stare anyway. For 10 days it gathered light from that single patch, photon by patient photon, never blinking. And when the image came back, it was not empty. It was full. Thousands of galaxies filled the frame, spirals, ellipses and blobs of light that had travelled billions of years to arrive. Each dot, each swirl was a galaxy, some older than Earth, some as old as time itself. The Hubble Deep Field image didn't just expand our catalogue, it expanded our imagination. If so much could be hiding in a space so small, how much more was waiting? This single image taught us a quiet truth, that darkness is rarely empty. It may only be a matter of waiting long enough and watching with the right eyes. And so, for more than 2 decades, Hubble continued to watch. It charted the births and deaths of stars, studied supernovae to measure the expansion of the universe, found exoplanets by their shadows, and became, in many ways, the poet laureate of modern astronomy. Its images graced textbooks, museum walls, and children's bedrooms. It changed what we thought the universe looked like, and reminded us that beauty was not a byproduct of science, but one of its earliest promises. But as with any tool, there were limits. Hubble was designed to observe visible and ultraviolet light, wavelengths similar to those our eyes perceive. It could look far, but only so far, and the earliest galaxies, the first stars, the traces of cosmic dawn, those whispered not in visible light, but in stretched, cooled infrared. Hubble's vision, though deep, could not reach those earliest flickers. It was like reading a novel and discovering that the first chapters were written in invisible ink. And so, scientists began dreaming of a successor. They envisioned a telescope that could see what Hubble could not. A telescope tuned not to brightness, but to warmth. Not to colour, but to age. One that could detect the faintest embers of the first stars, the earliest galaxies, and the dusty exoplanets hidden behind veils of gas. That dream became the James Webb Space Telescope. But JWST is not just Hubble 2.0. It is not simply a stronger version of what came before. It is something quieter, more specific. Where Hubble is a brilliant generalist, a versatile eye for many parts of the universe, JWST is a listener for whispers, a collector of faint warmth from faraway beginnings. Its mirrors are larger, yes. Its sensors are more sensitive, yes. But more than that, its mission is different. Hubble showed us the modern universe in stunning detail. JWST aims to show us the first universe, the universe before galaxies were galaxies, before stars were common, before dust and metals filled the void. Hubble showed us what is. JWST hopes to show us how it became, and the two are connected, not just scientifically, but emotionally. In a sense, Hubble taught us how to wonder again. After centuries of astronomy, of theories and math and chalkboards full of equations, it gave us images that felt immediate, tangible. It reminded the world that the cosmos is not a spreadsheet, but a story. That science is not just about solving mysteries, it is about living in their presence. JWST inherits that legacy, but with a quieter voice. It doesn't offer colour in the traditional sense, not bright blues or brilliant reds. Its palette is subtler. It sees in heat, in stretched light, in signatures that are not visual but spectral. Its beauty lies not in what we can immediately grasp, but in what we're still learning to interpret, and that in itself is beautiful. Because every telescope is not just a machine, it is a mirror, not of the stars, but of us, of our curiosity, our patience, our need to understand. Each one reflects a new level of ambition, a new willingness to wait for answers. From Galileo's spyglass to Newton's reflector, from Hubble's wide gaze to Webb's delicate hearing, each telescope tells us that wonder is not just a reaction, it is a responsibility. So when JWST opened its mirrors in 2022 and took its first images, it did so with a kind of inherited reverence. It was not the first to look up. It was continuing a lineage of looking, a quiet ritual passed down through hands, through questions, through generations. And when it began to find galaxies that shouldn't be there, too big, too old, too structured, it didn't betray that legacy. It honoured it. Because surprise is not failure. It is the engine of knowledge. Hubble gave us the stars. JWST gives us their ancestors. And in doing so, it gives us the chance to become better ancestors ourselves. To pass down not just facts, but the courage to look again. If you were to take a picture of the night sky and then try to weigh it, you'd find something strange. The light you see from stars, galaxies, nebulae is dazzling, intricate and vast. But it doesn't weigh enough. Not nearly. The visible matter, the things we can count and name and point to, simply can't account for the way the universe moves. And that's a problem, because galaxies don't behave the way they should if they're made only of what we can see. They spin too fast. When a galaxy rotates, the stars near the centre move quickly, as you might expect. But so do the stars at the edge. Not just fast, but too fast. So fast, in fact, that the galaxy should fly apart, flinging its stars like leaves in a windstorm. But it doesn't. It holds together, quietly, gracefully, for billions of years. And that means something invisible must be holding it in place. Something with mass. Something that exerts gravity. Something we cannot see. We call it dark matter. It is one of the strangest and most quietly powerful ideas in modern cosmology. Dark matter does not emit light. It doesn't reflect it, refract it, or absorb it. It passes through ordinary matter as though it isn't there. If you tried to catch it in your hand, it would slip through. If you built a mirror for it, it would ignore the mirror completely. It does not shine, and yet it shapes the universe more than any star ever has. How do we know it's there? We watch its influence, the orbits of stars around galaxies, the motion of galaxies in clusters, the bending of light around invisible masses like a funhouse mirror carved by gravity. These are the fingerprints of dark matter, the signs that something unseen is pulling on space itself. Imagine a landscape at night. You cannot see the hills or valleys, but you watch a river flow. If the water bends left, you know there's a slope. If it pools, you know there's a dip. You don't need to see the terrain to know it's there. You see how things move, and from that, you infer the shape of what's beneath. In this way, dark matter becomes the hidden architecture of the cosmos. It forms a kind of scaffolding, a framework upon which galaxies are built. Without it, the early clumps of gas and dust might never have formed stars. Without it, the cosmic web would not have emerged. Without it, structure itself might have been stillborn. And yet, despite its importance, dark matter remains elusive. No one has ever touched it. No detector has caught it directly. There are theories, of course, some elegant, some wild. Perhaps dark matter is made of new kinds of particles, undiscovered by the physics we know. Perhaps it behaves in ways that mimic mass without actually being mass. Perhaps our understanding of gravity is incomplete, and we've mistaken complexity for presence. But for now, the most compelling explanation is that something massive and invisible is out there, shaping galaxies like a sculptor working in silence. And perhaps that's the most beautiful thing about it, that the universe may be filled with something we cannot see, but which holds everything together, something that asks nothing of us, but gives us stars. James Webb cannot see dark matter directly either, but it can trace its influence by watching how galaxies form, how they cluster, how they warp the space around them. It listens for the shape of silence, the contour of the unseen, and in that listening it joins a long lineage of astronomers and physicists who've learned that sometimes the most important things are not the brightest, but the most enduring. There is comfort in this idea. That much of the universe is invisible, but not indifferent. That structure does not always come from the visible, that the stars are arranged not by what they burn, but by what surrounds them silently. Dark matter may never sparkle, it may never be touched, but without it, there would be no galaxies, no planets, no story. And so, when we speak of the cosmos, we speak also of what we cannot see, of the scaffolds, of the shadows, of the gravity that does not glitter but still holds us close. Perhaps that's why, in a way, dark matter feels familiar. We too are shaped by forces we don't always understand. Emotions, memory, longing, things that cannot be weighed easily but which define the orbits of our lives. And just as galaxies spin in the arms of the unseen, perhaps we also move through something invisible, some quiet presence that keeps us from flying apart. So as you lie still now, perhaps under a blanket or beside a quiet fan, let yourself feel the presence of what's not seen. Let it be a comfort, not a mystery. The world is full of gravity we don't understand, and that's okay. Because sometimes the things that shape us most are not the ones we see, but the ones we feel pulling gently from the dark. There was a time when we thought the universe might slow down, that after its rapid expansion from the Big Bang, gravity would gradually take hold, gently tugging galaxies toward one another, slowing their drift, perhaps even pulling everything back together in a long, quiet reversal. A kind of cosmic sigh. A return to stillness. That would have made sense. Gravity, after all, is patient and persistent. It pulls on all things, from falling apples to orbiting moons to the clustered galaxies at the edges of the known. For most of the 20th century, cosmologists believed that gravity would eventually win, that the universe was like a ball tossed into the air, rising at first, slowing over time, and eventually falling back toward its source. But the universe, as it so often does, had other plans. In the late 1990s, 2 independent teams of astronomers set out to measure the expansion of the universe more precisely. They used a specific kind of exploding star, a Type Ia supernova, as a cosmic yardstick. These supernovae are incredibly bright and remarkably consistent in their brightness, which means if you know how bright they truly are, you can figure out how far away they must be, just by how dim they appear. The plan was simple: find distant supernova, measure their light, calculate how fast the universe is slowing down. Except it wasn't slowing down, it was speeding up. The more distant the supernova, the faster its host galaxy seemed to be fleeing. Space itself wasn't just expanding, it was accelerating. This was a surprise not just in degree, but in kind. It wasn't just that the math had been slightly off. The entire assumption that gravity was the only force shaping the cosmos on the larger scales had to be reconsidered. And so scientists did what scientists do when they find themselves in unfamiliar territory. They gave the unknown a name. They called it dark energy. We don't know what dark energy is. Not really. It's not a substance. Not in the ordinary sense. You can't bottle it, weigh it, or touch it. It doesn't clump. It doesn't gather in stars or galaxies. It doesn't pull. It pushes. It acts like a pressure written into the very fabric of space, a subtle, persistent tendency for the universe to expand faster and faster, not dramatically, not all at once, but slowly, like a breath being drawn without end. In a way, dark energy is the opposite of gravity. Gravity binds, it gathers, it collects and curls. Dark energy unbinds, it spreads, it stretches, is not violent or explosive. It doesn't shatter or scatter. It's quieter than that. More like a breeze that never stops blowing, gently parting galaxies, widening the distance between stars, pulling the sky apart by millimeters and light years. And it's everywhere. Unlike matter, which forms clumps and filaments and empty voids, dark energy seems to be evenly spread throughout space. Every cubic meter of the universe contains a little of it. Not much. But because space is so vast, and because the universe keeps making more of it as it expands, the total amount of dark energy adds up to something immense. In fact, it now appears that dark energy accounts for nearly 70% of the total content of the universe. Add in dark matter, and the things we cannot see make up about 95%. That means everything we've ever observed directly, stars, planets, people, even telescopes themselves, make up only about 5% of what exists. The rest is invisible, untouchable, and deeply essential. And yet somehow, it doesn't feel frightening. There's a comfort in knowing that the universe continues to move outward. Not in panic, but in a slow and graceful unfolding. That its destiny is not to collapse in on itself, but to stretch gently towards something wider. It means that the galaxies we see today will drift ever farther from one another, that distant clusters will fade from view, that the observable universe will become quieter, more isolated, more local. It's a lonely thought, perhaps, but also an elegant one, a reminder that everything changes, that even space is not fixed, that even nothingness can evolve. James Webb, for its part, is not designed to study dark energy directly. That task falls to other observatories, like the upcoming Euclid telescope from Europe or NASA's Roman Space Telescope. But JWST plays its role. By observing the early formation of galaxies, it helps refine our understanding of how the universe evolved. By studying ancient supernovae, it contributes to our measurement of cosmic expansion. And by revealing the structure of the distant past, it helps us understand the invisible hand that shaped it. Dark energy doesn't sparkle, it doesn't leave trails, it doesn't bend light or cluster around galaxies. But it leaves a signature in the stretching of space, in the pace of time, in the quiet widening between everything and everything else. And in that widening there is something strangely poetic, a kind of cosmic exhale, a letting go. Perhaps we're not meant to fully understand it. Perhaps its nature is for now a whisper too soft to hear. But even that whisper moves worlds. So tonight, as space itself continues its patient expansion, you might think of the silence between stars not as emptiness, but as a breath, a presence, a slow, unfolding stillness. Dark energy doesn't ask to be seen, but it makes seeing possible. When you look up at the night sky, what you see is beautiful, but it is not the whole story. The stars twinkle, the Milky Way arches across the horizon like a veil, and planets move slowly, calmly through their ancient orbits. You might think, as many once did, that these glowing shapes represent the fullness of the cosmos, that everything real is also everything visible, but it isn't. In fact, the stars and planets, the gas and dust, the things that shine or reflect light, all of that makes up only a sliver of what the universe contains. Just 5%, give or take. The rest is made of shadows, not the kind that fall from trees or form behind mountains, but deeper shadows, fundamental ones, parts of the universe that have mass or energy or effect, but no light, no shimmer, no colour, dark matter, dark energy. They don't glow, they don't gather on mountaintops or drift through the sky. They don't announce themselves, and yet they form the shape of everything. They sculpt the galaxies, they stretch the space between stars. They are not decorations. They are structure itself. You might think that learning this, that 95% of reality is invisible, would be unsettling, that it would make the universe feel unknowable or cold. But the opposite often happens. Because once you understand that so much exists beyond what you can see, you begin to trust in what you cannot measure, not blindly, but quietly, not with fear, but with a kind of reverence. There's a tenderness in realizing how much we owe to things we've never touched. The galaxies would not have formed without dark matter. Their arms would not hold their stars. Their clusters would drift apart. There would be no scaffolding on which the cosmos could build itself. And without dark energy, the universe might have slowed, faltered, collapsed. Instead, it expands, softly, patiently, persistently. These invisible forces do not need our permission. They do not ask to be observed, and yet they leave behind a trail of consequences, bending light, shaping orbits, setting the pace of time itself. It is as though the universe were built by ghosts, not in the sense of the supernatural, but in the sense of presence without appearance, effect without form, a whisper behind the curtain, a hand that never shows itself, only the motion it imparts. Some people find this frustrating. They want certainty. They want evidence that fits in a box. They want particles we can detect, fields we can define. And of course, science keeps trying. experiments have been built to search for dark matter particles. Observatories scan the sky to better understand cosmic acceleration. The questions are alive. The work continues. But even without answers, the mystery holds value. Because it reminds us that knowledge is not a fixed state. It's a process, a reaching, a willingness to keep asking even when the answers are faint. There's a kind of humility that grows when you realise how incomplete your understanding is, not as a failure, but as an invitation. A space not yet filled, a dark canvas still waiting for the first stroke of light. And maybe that's the true gift of these unseen forces. They remind us that the universe is not finished. That even now, billions of years after the first stars, it still has secrets. That we live inside something still being written. Think of it like walking through a fog. You cannot see far ahead, but you know the ground is there beneath your feet. You know the air is still around you. You feel your way forward, one step at a time, not with fear, but with patience. Dark matter and dark energy are that fog. They surround us, they carry us, they shape the ground on which galaxies walk, and while we may not see them, we move through them all the same. James Webb cannot photograph these ghosts directly, but it shows us their influence in the way galaxies cluster, in the way light bends, in the history etched into starlight. And through its eyes, we begin to see not the ghosts themselves, but the footprints they've left behind. A curve in the sky, a stretching of space, a silence that speaks, and so, perhaps the universe is not a riddle to be solved, but a presence to be witnessed. Not everything needs an answer to be meaningful. Sometimes the act of wondering is enough. Because if 95% of the cosmos is unseen, then wonder itself is not just a feeling. It's a mirror, a way of holding space for what we do not yet understand. And maybe that's the most human thing of all. To live in a universe we don't fully grasp. To love what we cannot name. To trust gently in the architecture of shadows. So tonight, as you breathe in the stillness of your own room, or feel the gentle hum of your fan, or listen to the quiet edge of sleep beginning to blur your thoughts, know this: the stars you see are resting on the shoulders of things you cannot see. And those things, those quiet presences, are still holding you up. When you look at the stars, you're not really seeing them as they are. You're seeing them as they were. Light takes time to travel, and what you're witnessing is history, shining toward you from vast distances, carrying stories from across the universe. But it's not just a picture, it's a message. And like any message, it can be misunderstood. Astronomers don't see the universe directly. They see light, tiny packets of it, called photons, each with a specific colour, a specific energy, a specific path. That light has travelled for billions of years, through gas, through dust, through expanding space, before gently landing in a telescope's mirror. And the further it's come, the more it has changed. You see, the universe is expanding, and that expansion stretches space itself. As space stretches, so too does the light moving through it. Like a rubber band gently pulled, each photon's wavelength grows longer. What once was blue shifts toward red. This is known as redshift. Redshift is not just a shift in colour, it's a clock. The more redshifted the light, the older it is, the farther it's travelled. It tells us how long ago the light began its journey, and how much the universe has expanded since then. For cosmologists, redshift is a kind of time signature, an imprint left by motion, distance, and age. But redshift isn't the only thing that shapes the light. There is also dust. Not dust like what gathers on bookshelves or drifts in morning sunbeams, but cosmic dust. Tiny grains of carbon, silicates, metals, floating between stars and galaxies. This dust is born in dying stars, in supernovae and winds from giant suns. It's not alive, but it carries the memory of life, and it gets in the way. Dust doesn't block all light. It prefers to scatter the shorter wavelengths, blues and violets, letting the reds and infrareds pass through more easily. When light from a distant galaxy travels through a dust-rich region, its colour changes. It becomes redder, dimmer, altered. This creates a puzzle. If a galaxy looks red, is it because the universe expanded the light, or because dust along the way changed it? Or both? That's where telescopes like JWST come in. JWST doesn't just take pictures, it breaks light apart, separating it into its component wavelengths, like a prism spreading sunlight into a rainbow. These spectra are the fingerprints of the cosmos. They contain lines and gaps, signatures of elements, motions and temperatures. They help astronomers tell the difference between a galaxy that's truly ancient and one that merely looks that way because of dust. But even that isn't simple. JWST has many filters, each designed to capture a different slice of the infrared spectrum. By observing a galaxy through multiple filters, astronomers can build a rough picture of its colour and from that estimate its redshift. This technique is called photometric redshift, a way to guess a galaxy's distance by the shape of its light. But a guess is still a guess. To be more certain, astronomers look for spectroscopic redshifts, clear features in the spectrum that show how far the light is stretched. This method is more precise, but harder. It takes more time, more exposure, more patience. And sometimes, those features are too faint to find. So, for many galaxies, we rely on patterns, on models that say, if the light looks like this, it probably came from that far away. And most of the time, those models are good. They're based on decades of research. But they are still built on assumptions. What kind of stars does the galaxy contain? What is their age? How much dust lies in the way? Has the light been lensed, magnified by the gravity of something in front of it? Are we even seeing the whole galaxy, or just its brightest part? Each of these questions adds a layer of uncertainty. Not error, just complexity. And that's the quiet truth behind every cosmic image. It is not a snapshot. It is an interpretation, a decoding, a reading of a message written not in letters, but in wavelengths. Imagine receiving a postcard that had travelled for years, passed through storms and deserts, soaked in sun and bent at the corners. The ink has faded. The words are smudged. But you can still make out the message. You hold it close. You read between the lines. That's what astronomers do. They read the sky like old letters, with care, with love, with the knowledge that every detail might change the meaning. And JWST is the most sensitive reader we've ever built. Its instruments can detect the faintest signals, light that has travelled for more than 13 billion years, stretched into the deep infrared, whispering from a time when galaxies were still forming their first stars. But even JWST must interpret. Even JWST must choose which filters to use, which regions to observe, which assumptions to trust. It is not a camera, it is a translator, and that's what makes astronomy both science and art. It is not just about collecting photons, it is about giving them meaning. So when JWST finds a galaxy that looks too massive, too red, too old, astronomers ask, is it truly old? Or is the light playing tricks? Is dust masking the truth? Are we reading the letter, or just its envelope? These are not doubts, they are acts of care. Because science is not about being right the first time. It's about learning to see better, about refining the lens, not just the mirror, about listening more closely until the signal becomes clear. So as you rest now in the stillness of your own space, think of the sky not as a picture, but as a letter, folded many times, faded by time, but still reaching you. And if it arrives slightly smudged, slightly redder than it began, remember, it has come a long, long way, and it's still full of meaning. A galaxy appears on the screen. It is bright, distant, shaped more cleanly than you expected for something so far away. You measure its redshift, estimate its distance, and find, to your quiet astonishment, that this galaxy existed less than 1 billion years after the Big Bang, and yet somehow it already contains hundreds of billions of stars. It is, by every calculation, massive. Too massive, some might say, for its age. That's the puzzle James Webb confronted scientists with in its first months of observation. Galaxies that seemed not just old, but heavy, as if they had been building stars for far longer than the universe should have allowed, as if the cosmic clock had run faster for them than for everything else. But before rewriting the laws of cosmology, scientists did something subtler. They asked, what if the galaxy isn't what it seems? Because in astronomy, brightness does not always equal mass. A bright object can be small. A dim object can be large. What matters is how we convert light into meaning, and that conversion relies on assumptions, one of the most important being what kinds of stars we believe are in that galaxy. This brings us to a quiet, complex concept, the initial mass function, or IMF. The IMF is not a machine or an observation. It's a statistical guess, a model for what kinds of stars are formed in a given population. When a galaxy forms stars, not all of them are the same. Some are big and burn fast. Others are small and live for billions of years. The IMF tells us the likely distribution of these stars, how many massive ones, how many medium, how many tiny embers that may still be glowing today. For most of modern astronomy, scientists have used a fairly standard IMF based on observations of star-forming regions in the Milky Way. It works well. It gives decent predictions. It lets us translate a galaxy's light into estimates of how much mass it contains, and how many stars contribute to that light. But what if the early universe didn't follow that rule? What if the first galaxies, the ones JWST sees at the edge of time, formed stars differently? What if their IMF was skewed, favouring larger, brighter stars? In that case, the light we see might be coming from a smaller total mass than we assume. The galaxy looks massive, but it might simply be full of brilliant short-lived stars burning quickly and dying early. This isn't just speculation, it's plausible. The conditions in the early universe, denser gas, lower metallicity, higher temperatures, may well have favoured the formation of more massive stars, and if that's true, our measurements are off, not because the telescope failed, but because our conversion formula needs adjustment. It's like seeing a distant city at night and guessing its population based on how many windows are lit. If the lights are brighter than expected, you might overestimate how many people live there, but maybe they just use stronger bulbs. This is the delicate balance in astronomy. The light is real, the data is real, but the meaning we attach to it is filtered through models, through expectations that may or may not apply to conditions very different from our own. JWST has pushed us to revisit those expectations, and it's not just the IMF. Dust, redshift, gravitational lensing, all can distort how we interpret brightness. Even the geometry of a galaxy matters. A flat disk viewed edge-on may appear dimmer than it is. A burst of star formation can make a galaxy briefly outshine its size. Galaxies collide, stir up gas, trigger light shows that mimic greater maturity. The early universe was not a quiet place. It was turbulent, creative, messy. That messiness carries into our models, simulations of galaxy formation. Those virtual universes built by supercomputers often rely on simplifications. They have to. The real cosmos has too many variables to model perfectly, so scientists focus on trends. They build rule sets, how stars form, how gas cools, how dark matter clumps. These simulations are remarkable, but they're still guesses. Educated, tested, iterated guesses, but guesses all the same. When observations like JWST's reveal galaxies that don't fit, it doesn't mean the models are broken. It means they are being asked to grow. And that is how science lives, by being surprised and choosing to listen. So perhaps the two massive galaxies are not problems, They are teachers. Perhaps the light they send us isn't defiance, but refinement, a gentle correction in the language of photons. This does not make the universe less wondrous. In fact, it makes it more so, because it reminds us that even our best tools are only as good as our willingness to revise our beliefs. That knowledge is not a statue carved once, but a shoreline reshaped by each wave of discovery. You could spend your whole life building a map of the cosmos, and then have that map redrawn by a telescope 1.5 million kilometers from Earth, and still you would not be lost. You would be learning. And so, as you rest now, consider this. That galaxy you saw earlier, the one that seemed too big, too soon, it may be different than it appeared, but that doesn't make it any less real. It makes it more alive, not an error, an invitation. Every photograph is a choice, a frame within a larger world. You point your camera, you adjust the light, you focus on something that catches your eye, but there's always more outside the border, more that you don't see, more that the lens misses, more that light didn't reach. And in astronomy, the same is true. Telescopes are not passive observers, they are choosers, not in intent but in nature. They see only what they are built to see, only what is bright enough, large enough, or close enough to cross their threshold. And that means the universe we observe is not the full universe, it is the subset that reveals itself. This is especially true when looking deep into cosmic time. The early galaxies discovered by the James Webb Space Telescope seem extraordinary. They are luminous, structured, sometimes massive. They challenge our expectations about how quickly the cosmos assembled itself. But before concluding that these galaxies are somehow wrong, we must ask a quieter question. What if we're simply seeing the exceptions? In astronomy, this is called observational bias, the tendency to detect only the objects that are easiest to find. A bright galaxy will be noticed before a faint one. A concentrated burst of star formation will outshine a quiet, steady glow. Telescopes like JWST are incredibly sensitive, but they still work within limits. They have exposure times, filters, thresholds. They gather what light they can, but they cannot catch everything. Imagine standing at the edge of a dark forest holding a candle. You see fireflies flicker in the near distance, brilliant against the black, but you cannot see the beetles crawling quietly in the undergrowth. You might think in that moment that only glowing things exist, but you'd be wrong. You've simply seen what could be seen. In the early universe, the same might be true. The galaxies we detect at high redshift, the ones formed within the universe's first billion years, may be the brightest, most active ones. The show-offs, the fireworks, the ones with intense starbursts or massive black holes heating their cores. They flare into view because they shine hard and fast. But around them, perhaps even more numerous, are fainter, slower, quieter galaxies. Ones that JWST cannot yet resolve. Ones that will take longer exposures, different instruments, or deeper surveys to reveal. If that's the case, then the early universe may not be unusual. We may simply be seeing its most extroverted members first. Another bias may come from how we interpret redshift. As light from distant galaxies stretches, it shifts into the infrared. But the amount of shift must be estimated, especially when full spectral data isn't available. If we slightly overestimate the redshift of a galaxy, if it's a little closer than it seems, then we also overestimate its age and mass. A galaxy that looks impossibly mature at redshift 13 might be perfectly ordinary at redshift 10. That difference, in cosmological terms, is hundreds of millions of years. There are also lensing effects to consider. Sometimes a massive object, like a galaxy cluster, sits between JWST and a distant galaxy. Its gravity bends space and light, acting like a magnifying glass. The distant galaxy appears brighter and larger than it really is. We see it better than we otherwise could. But it also appears deceptively bold. Lensing is both a gift and a distortion. Astronomers know these things. They account for them when they can. But bias even when understood, remains part of the process, not as a flaw, but as a condition of being human. We do not see the universe as it is. We see it through instruments, through models, through time, and yet, within these limitations, there is still truth. The galaxies JWST reveals may not represent the average early galaxy, but they are still real. Their light is honest, their structure is meaningful, they exist, and that alone reshapes our understanding. Perhaps the most humbling idea is this, that we may be misreading not just the mass of these galaxies, but their age. A galaxy that appears well-formed and red might be interpreted as old, but it could simply be dusty or rapidly evolving. Its stars might be young but numerous. Its shape might come from gravitational mergers that happened faster than we thought possible. Or, most intriguingly, perhaps our expectations are too narrow. The standard models of galaxy formation, like the lambda CDM framework, predict a gradual build-up of structure. But if the universe had pockets of intense star formation earlier than expected, then some galaxies would look mature much earlier. Not because the model is broken, but because it allows for variation. In that sense, these strange early galaxies are not problems. They are data points at the edge of a bell curve. Outliers, but not errors. They ask us not to discard our theories, but to expand them. To remember that the cosmos, like a forest, contains both the fireflies and the beetles, and that it takes time to see them all. So as we continue to map the earliest chapters of cosmic history, we must do so with both precision and humility, with tools sharp enough to measure and hearts open enough to be surprised. Because what JWST is showing us is not just the galaxies that existed, but the limits of how we thought they should. And in that gap, between expectation and observation, new knowledge begins to grow. So tonight, as you drift toward rest, know that even our finest instruments are still learning how to see, and that's okay. The universe is not a picture, it is a story, and every frame we catch adds a new line, a new twist, a new softness to the way we understand it. Let it be incomplete, let it be alive. When you gaze up at the soft band of the Milky Way stretching across the night sky, it may look serene, like a quiet painting hung above the world. But behind that calmness lies motion, a slow, tidal shifting of stars, gas and dark matter that has been unfolding for billions of years. Galaxies do not stay still. They move, they pull, and sometimes they consume. Right now, as you lie here listening, our own galaxy is in the process of eating another one. It's called the Sagittarius Dwarf Galaxy. Smaller, dimmer, and far more fragile than the Milky Way, it has long been drifting through our galactic halo. Over time, gravity stretched it into a ribbon of stars, its shape distorted, its orbit decayed. Bit by bit, the Milky Way's gravity has been tearing it apart, absorbing its stars, mixing its material, folding it into our own spiral. This process is not sudden. It takes millions of years. There is no crash, no explosion. It is more like fog dissolving into air or a stream joining a larger river. The smaller galaxy becomes part of the larger one, not erased but incorporated. And this is not unusual. Galactic cannibalism, as it's called, is one of the primary ways large galaxies grow. Over cosmic time, bigger systems draw in smaller ones. They feed not with hunger, but with gravity. They stretch and scatter, then gather and fuse. These mergers bring in new material, fresh gas for star formation, new orbits, new motion. They reshape galaxies, sometimes igniting new arms or forming glowing halos. The Milky Way has done this many times. It likely began as a much smaller galaxy, building itself over billions of years by absorbing others. Like a tree growing rings with each season, our galaxy carries layers of history, stars that once belonged to other systems, now orbiting quietly within ours, and we're not done. In about 4 billion years, the Milky Way will meet Andromeda, our largest neighbouring galaxy. Right now, Andromeda is faintly visible from Earth, as a smudge of light in the northern sky. It lies over 2 million light-years away, and yet it's getting closer. Slowly, inexorably. The space between us is shrinking. When they finally meet, it won't be a collision like cars on a highway. Stars are spaced far too widely for direct impacts, but their gravitational fields will interact. Tides of gas will stretch. Orbits will shift. New stars may be born in great waves of compression and collapse. And over time, the two galaxies will merge into one. A new, larger galaxy, sometimes called Milkomeda. It sounds dramatic, but really, it will be beautiful. Even now, astronomers simulate these mergers on computers, watching spiral arms twist into tidal tails, watching cores dance and settle, watching chaos become structure. These are not acts of destruction. They are acts of becoming. Like rivers joining, like fabrics weaving together. And through all of this, accretion, collision, merger, new stars continue to shine. In fact, some of the most brilliant bursts of star formation happen during galactic encounters. Gas clouds, jostled by gravity, collapse more easily. New suns ignite in clusters, lighting up the darkness with brief, bright lives. So when JWST looks out into the universe and finds galaxies that seem large and luminous in the early cosmic eras, we now suspect that some may have grown this way, not alone, but in communion, through contact, through complexity, through the patient gathering of parts. It's tempting sometimes to think of galaxies as solitary islands, but they are not. They are more like drifting cities, expanding, absorbing, influenced by every passing neighbour. Even the voids between them shape their motion. Even the smallest companion can leave a fingerprint. There is something deeply poetic in this idea. That growth does not always mean keeping things out. That sometimes it means letting other things in. Even now, as you lie here beneath the quiet of your own sky, the stars above you include those from other galaxies. Immigrants, wanderers, particles of a long, slow dance that began long before Earth had oceans and will continue long after Earth has clouds. You're part of a galaxy that eats, but also a galaxy that remembers. The stars of Sagittarius Dwarf still trace their origin, even as they join the Milky Way. Their paths are not erased. They become part of a new whole, but they carry echoes of where they came from. Astronomers can still trace them, streams of stars flowing through the halo, like ghosts drifting through a memory. And when Andromeda arrives, it too will bring its own echoes, and in the far future, whatever beings look up from whatever world survives, they may see a new galaxy, massive, majestic, and wonder where it came from. They won't see the separate parts, only the final harmony. So perhaps, as strange as it sounds, there is kindness in this process, a kind of cosmic generosity. Not all mergers are violent. Some are patient, some are creative, some build something greater than what existed before. And if galaxies can do that, why not us? It's easy to imagine space as random, a scattering of stars, a chaotic sprinkle of galaxies across an endless sky. But the more carefully we look, the more we realise that the universe is not disorderly. It is deeply patterned. Not in the way a city grid might be planned, but in a more organic, more ancient way. A cosmic architecture woven not by intention, but by gravity, time, and the ghost-like pull of dark matter. Our own galaxy, the Milky Way, is not floating in isolation. It is part of a local group, a family of more than 50 galaxies bound together by mutual gravitational attraction. Some are large, like Andromeda, some are small, like the dozens of dwarf galaxies that circle both us and our neighbours like quiet moons. They all drift, dance, and occasionally embrace, connected by invisible threads of dark matter and shared momentum. From the perspective of this group, we are in a kind of celestial neighbourhood. We know the neighbours, we know the direction of traffic, We can trace the history of interactions and predict future collisions. The local group spans about 10 million light-years, a comforting region of space that, though unimaginably vast, feels intimate in cosmic terms. But our group is just a room in a much larger house. Step back and you find that the local group itself is part of the Virgo supercluster, a gathering of dozens of galaxy groups and clusters, stretching out over 100 million light-years. This structure is not a sphere or a disk. It's something more like a braid, a strand of cosmic material following invisible filaments. Galaxies within it are not strewn like confetti, but line up in long arcs and walls, separated by vast empty voids. And even that is not the whole picture. Zoom out again, and the Virgo supercluster becomes part of something even larger, a structure called Laniakea, a name that means immense heaven in Hawaiian. Laniakea encompasses more than 100,000 galaxies, all connected, all flowing toward a gravitational centre called the Great Attractor. It is a basin of motion, not of matter, a place where space itself seems to lean in. What emerges from this view is a sense not of chaos, but of flow. Galaxies are not random dots. They are more like leaves carried on cosmic rivers, gently pulled by invisible currents. Those currents form what we call the cosmic web, an enormous three-dimensional lattice of filaments and knots and voids, where galaxies gather like dew on spider silk. And at the largest scale, that web is our home. It's strange to think that something so vast can also be so structured, but it makes sense. At the very beginning of the universe, tiny fluctuations, imperfections in the otherwise smooth energy field, were stretched and amplified by inflation. These became the seeds of galaxies, the scaffolding for everything to come. Dark matter gathered around them, gas followed, stars were born, and the filaments grew. It's humbling to realise that we are not just in a galaxy, not just in a group or a cluster, but in a pattern that began almost immediately after the Big Bang. A thread in a tapestry that was woven before there were stars, before there were atoms, before there was light. And in that tapestry we are not central. We are not even particularly special. But we are real. We are part of the design. And sometimes being a thread in something beautiful is more meaningful than being the centre of anything. James Webb helps us map this structure, not just by capturing images of distant galaxies, but by measuring their motion, their clustering, their shape. With each observation, we refine our map of the universe's skeleton. We trace the flows. We see how galaxies form not alone, but together, fed by rivers of cold gas, shaped by ancient motions, illuminated by stars that flare and fade and begin again. There is something profoundly comforting in this idea that we're not drifting. We are part of a system, a quiet choreography on a scale so immense it stretches the imagination. And yet, it's happening around us right now, in silence. It's easy to feel small in the face of all this. But perhaps that smallness is not a burden. Perhaps it's a kind of freedom. To know that you are not the architect, but the thread. Not the builder, but the music carried by the wind. Because if the universe is a web, then you are in it. Your atoms came from stars born in filaments. Your world orbits a star that is one spark among a billion others, flickering gently in a spiral arm of a galaxy, gliding through a supercluster, floating in Laniakea, falling toward the Great Attractor. And still, you are here, resting, listening, thinking, wondering. That is your motion. That is your thread. There is a quiet humility built into science, though you may not always notice it at first. It doesn't wear robes. It doesn't stand on podiums proclaiming truth. It begins, more often than not, with someone squinting at something and whispering, "That's odd." Odd is where it starts. And throughout the history of astronomy, perhaps more than any other science, this pattern repeats. We look up, we draw a map, we feel confident, and then the sky gently changes the subject. It happened with Ptolemy, whose geocentric model placed Earth at the centre of the cosmos. The sun, the stars, the planets, all circling us in perfect loops, epicycles upon epicycles, a majestic dance choreographed around our importance. For centuries this seemed obvious. And then came Copernicus, who nudged the sun into the centre instead. Not with fanfare, not with violence, just with math and a shift of perspective. It happened with Newton, who gave us a vision of the universe built from forces and motion. Clockwork elegance, cause and effect, every action paired with a reaction. And it worked beautifully, until a small discrepancy in Mercury's orbit hinted at something more. Until a beam of light refused to bend the way Newton said it should. And then came Einstein, who unwrapped space and time into something fluid, something curved by mass and energy. Even Hubble surprised us. The universe was not static, not eternal. It was expanding. The galaxies were running away from each other, carried by space itself stretching outward. The universe had a beginning. Time, it seemed, had a past tense. And now, with the James Webb Space Telescope, we find ourselves surprised once again. Not betrayed, not shattered, just asked to look again. When JWST began sending back images of distant galaxies, massive, structured, chemically rich galaxies formed within the first billion years, it sent ripples through the field of cosmology. These galaxies seemed too mature, too soon, as if someone had skipped ahead in the book and left notes in the margins we hadn't written yet. Some headlines shouted of a crisis, of a cosmological collapse. But if you listened closely to the scientists themselves, most were not panicking, they were smiling, because this is how science works. It doesn't fail when its predictions falter, it succeeds, because the moment the sky says, not quite, we are handed something better than certainty. We are handed a chance to learn, and that's the real tradition, not of being right, but of being surprised. Surprise is not the enemy of science, it's the prize, the crack in the wall where light gets in, the gap between what we thought and what the universe gently reveals instead. JWST is not the end of our models, it is the next conversation, the next refinement, the next fold in the ever-expanding paper of the cosmos. Some of the surprises will be smoothed by new explanations, adjusted models, better assumptions, a clearer understanding of how stars behave in the early universe. Others will remain open questions for decades, drawing new thinkers into their orbit. And all of it is beautiful, because science is not a fortress, it is a raft, built to float, to flex, to travel. It carries us, but it doesn't claim to anchor us. It invites us to move. Even the words scientists use reflect this humility. Theories are not facts, they are frameworks. Models are not final, they are tools. Hypotheses are not certainties, they are ideas offered up to the universe to be tested, changed, even discarded if necessary. There is poetry in that. A rhythm of asking, revising, asking again. It's not a flaw in the process, it is the process. And it doesn't mean we know nothing. Quite the opposite, it means we know how to listen. And what a remarkable thing to listen to light. To build an instrument like JWST and send it 1,000,000 miles into space, and then sit in patient silence, waiting for photons older than memory to tap gently on our digital mirrors. The universe doesn't scold, it doesn't laugh, it just speaks, and it keeps speaking long after we think we've heard it all. The first time we thought the sky circled the Earth, we were wrong. The first time we thought the stars were holes in a dome, we were wrong. The first time we thought the universe was unchanging, we were wrong. And now, as we look back to the earliest galaxies and find them more complicated, more luminous, more evolved than expected, we may be wrong again. But what a lovely, hopeful kind of wrong it is. A wrong that opens doors, that lights a candle, that builds a better question. So tonight, if you feel like the world is too complex to understand, remember, that's not a sign of failure. That's a sign of participation. You are part of a tradition that moves not by knowing everything, but by being willing to ask again. In the end, being surprised means we're still learning, and learning means we're still alive. All this time, we've been speaking of galaxies, of stars, of photons older than memory. We've traced their paths, followed their arcs, tried to understand what they are, where they come from, and how they grow. But somewhere along the way, it's worth pausing to ask, who exactly is doing the asking? You are. You, listening here, resting perhaps in the hush of your room, the weight of the day beginning to lift, the world softening around you. You are not just outside this story. You are inside it. You're not observing from the edge. You're stitched into the fabric. Because your body, your thoughts, your very breath are all built from the same material JWST seeks in the earlier stars. The calcium in your bones, the oxygen in your lungs, the iron that carries your blood's warmth. None of it was made on Earth. All of it was born in stars, not stars like our sun, older ones, stranger ones, stars that lived fast and died young, exploding in tremendous waves of heat and light, scattering their ashes into space. Those ashes floated, they gathered, they cooled, they formed new clouds, new stars, new worlds. Eventually one of those worlds formed oceans, and in those oceans chemicals began to copy themselves. Over time they became cells, then fish, then creatures who walked, then creatures who wondered, and now you. A being made of question marks. There is a quiet beauty in that. You're not just made of stardust in the poetic sense, you're literally composed of atoms forged in ancient furnaces now invisible, their light stretched by time, their memory recorded only in photons. And JWST? It collects those photons. It reaches into the past, catches light that left its home billions of years ago, and folds it gently into images and data, into meaning. That light had no idea you would be here to catch it. It did not aim itself at us. But still, it came, and still, you are here to receive it. Every photon is a message, not a sentence, not a story, but a whisper, a fragment of a moment, an echo, and it travels through silence, across time and space, to land in the retina of a telescope, or the eye of a person, where it becomes something more. It becomes knowledge and wonder. In that moment, you and the universe are not separate. You are a loop. The universe gave rise to stars. Stars gave rise to you. And now, you look back at the stars. You're not outside of the cosmos, studying it from a safe distance. You are the cosmos studying itself. You are what the universe does when it dreams, when it tries to understand what it is, when it learns to name things and measure time and feel awe. And awe is not a weakness. It is not a lack of knowledge. It is the recognition of how vast the knowledge could be. It is the pause before the question, the breath before the answer, the silence that surrounds understanding and makes it real. JWST is not just a telescope. It is an extension of that awe, of that question. It is the eye we built to see further than our ancestors ever imagined, and it did not disappoint us. It showed us galaxies we did not expect. It reminded us that we still have more to learn, but more than that, it reminded us of why we learn, because we are made to ask, not just as a curiosity, but as a way of being. Every child who looks up at the stars and asks what's that, is participating in this tradition. Every artist who paints a galaxy, every writer who imagines another world, every dreamer who falls asleep wondering if someone else far away is looking back. And maybe they are. Maybe somewhere, in a galaxy, JWST just revealed to us someone else is doing the same. Or maybe not. Maybe we are alone for now. But even alone, we are part of something immeasurably large and inexplicably beautiful. And that is enough. That we are the question, not the answer, not the map, not the chart, the question. And to ask quietly, honestly, with no guarantee of an answer, is one of the most noble things the universe has ever done with itself. You're not here by mistake. You're not made of ordinary matter. You're made of story. A story that is still unfolding. A story that began in fire and continues now, in breath. A story that remembers itself every time you wonder. And that, maybe, is the most profound truth of all. That when you ask, what is out there? What you're really asking is, what am I part of? And the universe answers, not in words, but in light. The telescope is still watching. High above Earth, in a quiet place where gravity and sunlight find balance, the James Webb Space Telescope floats, a whispering eye fixed on the past. Its golden mirrors reflect nothing back toward us. Instead, they are angled outward into shadow, into silence, into the ancient glowing threads of the cosmos. Every day, JWST sends back more images, more light, more stories stitched from photons that began their journey before Earth even had oceans. Each one is a small act of time travel, not backwards through time as we imagine in fiction, but forward through patience. The universe did not hide its beginnings. It simply placed them far enough away that we had to grow into the ability to see them, and now we can. We can see galaxies that seem too old, too large, too composed to fit the neat predictions we once held. But perhaps they are not too old. Perhaps they are simply beautifully unexpected. Science was never meant to fit perfectly inside our expectations. It was meant to stretch them, to unravel assumptions, not rudely, but gently, like sunlight through lace, like a tide lifting the edges of a sleeping shoreline. And what JWST has given us is not a contradiction, but an invitation. A reminder that the cosmos is deeper, richer, and more varied than our best simulations could dream. Some galaxies are not behaving. Good. The universe is not obligated to behave. It is not a classroom. It is not a spreadsheet. It is a living history written in light, constantly reshaping itself in our perception. The galaxies that seem mature too early may not be mistakes. They may be truths we're just now capable of receiving. And still, the telescope watches. Its sensors, cooled to near absolute zero, feel the warmth of starlight born billions of years ago. Its mirrors, carved and polished with incredible precision, unfold quietly in the vacuum, untouched by atmosphere, untethered from earthly time. Its data travels homeward at the speed of meaning. And on the other end, here we listen. You too are a mirror, not of gold and silicon, but of thought and breath. A mirror of curiosity, of wonder, of quiet questions that bloom in darkness. You reflect the universe every time you wonder how it began. You hold its history every time you look up and let yourself feel small. That smallness is not a failure. It is a kindness. Because only things that care about the story feel small within it. The galaxies JWST sees will continue to reveal their secrets. Not in a flood, but in gentle waves. Some will take years to fully understand. Others may remain puzzles for generations. That's part of the rhythm, the way the universe teaches. It doesn't rush, it doesn't shout. It opens slowly, like a flower turning toward morning. So sleep now. Let the stars do the watching for a while. Let the galaxies keep drifting and glowing, far beyond worry, far beyond your reach, but never beyond your belonging. You are made from them, not just chemically, but emotionally. The need to know, to look, to reflect. That is starlight, still burning. And when you close your eyes tonight, you join a lineage of beings who wondered. You become one more mind in a long, unbroken chain. From the first creatures who noticed the sky, to the engineers who launched JWST, to the scientists decoding its signals, to the quiet moment you are living now, letting it all settle into stillness. You're not outside this story. You're the page it's written on. So rest, little mirror of the cosmos. The sky is not waiting for you to understand it all. It's simply asking you to stay curious, to keep listening, to wake again with questions, and to remember, always. The universe remembers too. Even the light you never saw, even the stars that have already died, even the dreams you thought were too small to matter, they are folded into the fabric. Sleep well, under stars that remember.